In practice, we will need to take account of more complex situation in which we have losses in the atmosphere due to attenuation by oxygen, water vapor, then rain, losses in the antenna at each end of the link, and possible reduction in antenna gain due to mispointing. All these factors are taken into account by the system margin but need to be calculated to ensure that the margin allowed is adequate. More generally, the link equation can be written in this way by considering different losses. PR equal to EIRP plus GR minus LP that we have already uh, described. Now we have to add some more losses, and we said that all the losses are actually subtracted. That is why all these losses along with the negative sign. Okay, so we have to add LA, LTA and LRA, where LA is the attenuation in atmosphere. Atmosphere means atmospheric constituents gases, actually water vapor, then oxygen, lots of constituent gases are there, vapors are there. They actually absorb some portion of the electromagnetic wave. So LA accounts for that. LTA, losses associated with transmitting antenna, and LRA is actually the losses associated with the receiving antenna. Once a value has been calculated in decibel, it can readily be scaled if one parameter is changed. Like if we calculated GR for an antenna to be say 48 dB at a frequency of say 4 gigahertz and wanted to know the gain at 6 gigahertz, we can multiply this GR by 6 by 4 whole square. Now in decibel unit, we can simply add 20 log 6 by 4, that is 20 log 3 minus 20 log 2, that is 3.5 dB. So the gain of the same antenna at 6 gigahertz will become 51.3 decibel. Right. So it is very easy to calculate or convert the gain expression or value of the gain, the loss, the receipt power, all these are very much easy in decibel. That is why decibel is used in satellite communication system. So basically this is a pictorial view of the equation that we have derived. So basically we are assuming this this is the transmitter part, this is the transmitter part. So PTGT is the effective isotopic radiated power, and the antenna has a loss of LTA, transmitter antenna loss. Then we have a path loss. Path loss is associated with LP, right? Along with there are some other losses, atmospheric losses, absorption, mainly absorption losses, that is written as LA, and we have a receiving antenna right here associated with the loss LRA, right? So all the losses are there, and the receive power right here, just at the end of antenna and beginning of the next stage, that is the LNA. Here we have the receive power PR. So that's the relationship between the transmitted power and the receiver power, receive power. Let us solve a numerical problem for basic transmission theory. A satellite at a distance of 40,000 km from a point on the Earth's surface radiates a power of 10 watt from an antenna with a gain of 17 dB in the direction of the observer. Find the flux density at the receiving point and the power received by an antenna at this point with an effective area of 10 meters square. Using the basic equation for flux density, F equal to PTGT by 4 pi r square, putting all those values, all the values are given here, we got this value. Now, if the collecting area is 10 meters square, then flux density multiplied by area will give you the received power. Okay. Now, if we use decibel, then you will see the calculation becomes much more easier. We have to remember that 4 pi log of 4 pi is 11 dB. So F in decibel unit, it will be PTGT minus 20 log R minus 11. So it becomes minus 136 dB watt per dB. Original unit was watt per meter square. Now it is dB. Then receipt power becomes minus 136 plus 10. So minus 126 dB watt. So calculation becomes very easy. You can do it by yourself without using any sort of calculator. But for this case, you have to use calculator. Okay. Let us solve another numerical problem related to basic transmission theory. The satellite in previous problem operates at a frequency of 11 GHz. The receiving antenna has a gain of 52.3 dB. Find the received power. So PR equal to EIRP plus GR minus path loss. EIRP is 17 dB watt. GR is 52.3 dB, and path loss that we can calculate, that turns out to be minus 205.3 dB. So PR becomes 27 plus 52.3 minus 205.3, that is minus 126 dB. So we have the same answer in the previous problem, because the figure 52.3 dB is the gain of 10 meter square aperture antenna at a frequency of 11 gigahertz. Okay. Now PR equal to EIRP plus GR minus LP in decibel unit. This equation with other parameter for antenna and propagation losses is commonly used for calculation of receipt power in a microwave link and is set out as a link power budget in tabular form using decibels. This allows the system designer to adjust parameters such as transmitter power or antenna gain and quickly recalculate the receipt power. The receipt power PR is commonly referred to as the carrier power, written as C. This is because most satellite links use either frequency modulation for analog transmission or phase modulation for digital digital transmission. Mostly PSK, QPSK type of modulations are used. In both of these modulation systems, the amplitude of the carrier is not changed when the data are modulated onto the carrier. So received carrier power C is always equal to the received power PR.